I hope that you had time to practice a little bit about the vectors sections that we talked about. So in this section, which is section 3.5, I'm going to talk about the position, displacement, velocity, and acceleration vectors. Let's begin with imagining a two-dimensional coordinate system. So I'm going to draw this system here. Like usual, I have positive x to the right and positive y direction that points upward. Now, if I want to show a position vector from origin to the location, it's enough that I draw the vector r. Okay, so the unit for this vector, because it's a position vector, is in meters. If I want to write this vector in its component form, and this is what we're going to do from now on, it's enough that I just break this into this component. So I know that this is Rx and this guy here is Ry. So for simplicity, let's just call Rx to be x and Ry to be y. So I can write the vector of position to be the magnitude of Rx, which is x in x hat direction, plus the magnitude of Ry in y hat direction. Okay, so this hat, when it is on top, it means that these are unit vectors. So I can define the x unit vector, or x hat, which means that it has that hat on top of it, to be a dimensionless vector of unit length pointing in the positive x direction, and then the y hat, or the unit vector y, is a dimension vector of unit length pointing in the positive y direction. So when we're talking about unit length, for example, in this case, it is 1 meter, right? Because our unit is in meters, so the unit vector should be in 1 meter or equal to 1 meter. Then I can just break every vector to its component and write it with the unit vectors. For example, if vector A is 5 meters, x hat direction, plus 3 meters in y hat, let me put this in capital, in y hat direction, this means that I have an xy coordinate. So 5 meters, imagine that this is 1, 2, so this is in meters, this guy is in meters, 3, 4, 4, 5, and then 3 meters in y hat direction. So this means that my vector A is right here. And then the unit vector is this guy. So this is x hat, and this is, oops, again, just trying to write it in capital form so I can differentiate it with its magnitude. Now, suppose that initially you're at the location indicated by the position vector Ri. Now, the subscript I stands for initial. So let me say that you're here, Ri, right? And then later you are at the final position represented by the position vector Rf, and again subscript F stands for final. All right, so if this is your final position, all right, now here your displacement vector let me call it by delta R, is the change in the position. So it is going to be RF minus RI. Oops. RI. Okay. So remember that when we wanted to subtract the vectors, we were going to write them as positive, negative RI, right? So plus negative of RI. So it's gonna be a vector like this. So this is your displacement vector, delta R. Or I can just rearrange this and write it to be R final equals to delta R plus R initial. I don't know what's wrong with me putting that hat instead of the arrow. Okay. So, and then let's check it. Ri plus delta R. So Ri here plus delta R, it gives you the R final, right? So this is correct. And then if you remember, I was defining the average velocity, V average, to be delta R, or displacement divided by time. Okay, the unit for this was meters per second. Since delta R is a vector here, it follows that also the average is a vector. So that is the vector delta R multiplied. So this means that delta R is multiplied by 1 over delta T. And because this guy here is a scalar, and then delta R is a vector, this makes the V average to be a vector. Okay, so it's just a matter of the magnitude, not the direction. So I can show delta V to be in the same direction, not delta V, but I can show V average to be in the same direction as the displacement, just it's gonna be smaller because it is now divided by time. So it is just smaller. Let's look at an example. Quick example 3.7 says that a dragonfly is initially at the position Ri, so this is the known of the problem, equals to 4.60 meters x hat plus 0.960 meters y hat, as shown in the sketch. So let me just go ahead and sketch this for you. After 3 seconds, so I have t equals to 3 seconds, the dragonfly is at the position RF equals to 520 meters in x hat direction plus 2.40 meters in y hat direction. Now, what was the dragonfly's average velocity during this time? So the unknown is the V average. Find this. Okay, so let me go ahead and just draw the R final too. Okay, so if this is almost 4.6 meters and this is almost 0.96 meters, then the x or the x component of our final is only around half meter. So it's going to be like very smaller. So it's going to be somewhere here. And then the y component is much bigger than the y component of our initial. So it's going to be somewhere around here. So this is going to be my R final, or the final position. Okay, so what I need to do in order to find the average of velocity is first of all to calculate the change in the position. So I'm going to need to find delta R to be R final minus R initial. And if you remember, I told you that for such a thing, we need to subtract the x component separately and the y component separately. So I'm going to subtract the x component first. So it's going to be 0.52 meters minus 4.60 meters for x hat plus, and now I'm going to subtract the y components. So the y component for our final is 2.4 meters minus the y component of our initial is 0.96 meters. And this is for the y component. All right. So then delta r is going to be negative 4.08 meters in x direction plus 1.44 meters in y direction. Okay, so again, x hat and y hat are the unit vectors, so they show the direction of the components. All right, now that I have the change in the position, I can go ahead and divide this by the elapsed time to find the V average. So V average is delta R divided by delta T. So it's going to be negative 4.08 meters in x hat direction plus 1.44 meters in y hat direction, all divided by 3 seconds. So this is again going to be 1 by 1. So the whole result is going to be negative 1.36 meters per second in x hat direction plus 0.48 meters per second, oops, squeezing here, in y hat direction. All right, so you need to have all of this together. Okay, I rewrote it for you so that you can just see it better. Another example now is exercise 3.8. So it says find the speed, okay, unknown. Find the speed and the direction, meaning the angle of motion for a rainbow trout whose velocity is, so the known of the problem, the velocity is given to be 2.6 meters per second in x hat direction plus negative 1.9 meters per second in y hat direction. All right, so this seems to be the opposite of the previous example. Now I have the components. I want to find speed, and remember that the speed was the magnitude of the velocity. Okay, so according to what we had before, to find the speed, I just need to use this equation here. Square root of the x component squared, which is 2.6 meters per second squared, plus the y component squared, negative 1.9 meters per second squared. So that gives us 3.2 meters per second. And now I want the direction. Now we can find the direction of motion using the inverse tangent, if you remember that theta was tangent inverse of the y component over the x component. It's going to be the tangent inverse of negative 1.9 meters per second divided by 2.6 meters per second, and then the calculator calculates this to be negative 36 degrees. Okay, so the trout moves at the rate of 3.2 meters per second in the direction of 36 degrees below the x-axis. So this means that it is moving, if this is x and y, so it's moving in this direction, right? So this is theta, negative 36 degrees. Finally, we need to talk about the average acceleration vector over the interval of time. So acceleration, if you remember, the average acceleration, we defined it to be the change in velocity divided by time. Okay, the SI unit was meters per second squared. So this means that the change in velocity, if it is the V final, and I'm using the same notation here, so the subscript F, it means the final velocity minus the initial velocity, then I can say that the final velocity is going to be delta V plus initial velocity, and then I can define the acceleration to be this change over the elapsed time. Let's just draw this. Let's say that I have X and Y, and then I have a particle that moves along this path. Okay, so I have, let's just draw a path for it. Okay, so if the particle, the initial velocity is in this direction, so let me call this initial velocity, and then so I'm just looking at 2 points, this point and this point. So the final velocity is in this direction, right? So I'm just gonna find the change in the velocity, but in order to do that, what I need here is that I need to draw the VF exactly beginning at the same point as VI. So this is, or let me, it should be tangent. So let me just draw it a little better, maybe. Try my best here. Okay, so maybe in this direction. Okay, so this seems to be more correct. So this is my path, this is my final velocity, and I'm going to exactly draw the same vector, same direction, same magnitude. But because I want to find the change, they need to start from the same point. Okay, so this is same, right? Now VF minus VI is going to be this vector here. So this is delta V. So it happens that the acceleration is in the same direction. So the acceleration should be vector right this, the average acceleration between these 2 points, P1 and P2, for example. Why? Because the average acceleration is just the change in the velocity divided by time. So it's going to be smaller than the change of velocity because we are dividing it by a positive number. Okay, so just notice that delta V is the vector that we extended from the head of VI to the head of VF, just as the delta R extends from the head of RI to the head of RF. Now, the important question here is, can an object accelerate if its speed is constant? And I'm going to leave the answer to this question for you to discuss it on the discussion board. Okay, but here is where you can think about it, and then you can also study page 74 on your book, which talks about it more. So this is section 3.6, a good example of the use of vectors in the description of relative motion. Okay, so suppose, for example, that you're standing on the ground as a train goes by at 15 meters per second. I'm going to draw the picture here for you. So here is my X and Y, and then, excuse me, but this happens to be you. And then you have a train. So this is a train that goes by 15 meters per second. Okay, inside the train there is a person, and that person is walking in the forward direction at 1.2 meters per second relative to the train. Okay, so let's consider that here there is another person, okay, and this person is walking at the rate of 1.2 meters per second forward. Okay, now this 1.2 meters per second is relative to the train. How fast is this person moving relative to you? Okay, so clearly the answer is 15 meters per second plus 1.2 meters per second equals to 16.2 meters per second. So that is the relative velocity relative to you as an observer. Now, what if the person had been walking with the same speed but toward the back of the train? Now, in that case, you would see the person going by with a speed less than the speed of the train, right? So I'm going to draw that situation again here. So if it was the same situation, X and Y, and guys, here you are again, and then you have a train, hopefully the same number of wheels. Okay, 15 meters per second is the speed of the train that passes by you. And then now you have a person inside the train that is going backward. Okay, then what is the velocity of this person relative to you? So then it's going to be 15 meters per second minus 1.2 meters per second equals to 13.8 meters per second. Now, this is only in one direction or in x direction, but let's go ahead and generalize the results. Let me call the velocity of the train, velocity of train relative to the ground to be v sub t g. So this means train relative to the ground. Now, the velocity of the passenger, meaning the guy on the train, relative to the train, I call it V passenger relative to train. And then I have the velocity of passenger relative to the ground. So obviously this is V, P, G. Now, as we saw in the example, the velocity of the passenger relative to the ground, which means you on the ground, is equal to the velocity of passenger relative to the train plus the velocity of train relative to the ground. Okay, so do not get yourself confused. So look at this P and G here, then you have P and T and T and G. So it just like follows a path. Now, if I want to illustrate this in vector form, I can draw this as the following sketch. So I can say that the velocity of passenger relative to the train is here, and then the velocity of train relative to ground is here. So the velocity of passenger relative to ground is this vector, right? So this should be exactly the same. Okay, if he's walking backward, then I have the velocity of passenger relative to train in this direction, and then I have the velocity of train relative to ground is in this direction, so the velocity of passenger relative to ground is only this much. Okay, let me go ahead and solve an example for you. Suppose the person in that previous example is climbing a vertical ladder with a speed of 0.24 meters per second, and the train is slowly coasting forward at 0.68 meters per second. Okay, so what I know is that the velocity of the train relative to ground is 0.68 meters per second. And then what I have here is that the velocity of the person relative to the ground, the velocity of person relative to train, because he is climbing the ladder inside the train, is 0.24 meters per second. But then the train is moving in this direction and the person is climbing up. Now find the speed and the direction of motion of the person relative to the ground. So what we want to know is that the velocity of person relative to ground, how much it is. Okay, so let's first thing visualize it, sketch it. So X and Y here, and then I have my 0 here, and then we have a train that is moving with velocity tg, meaning train relative to ground, and I have a person here who is climbing up, right? So this is the velocity of person relative to train. Okay, so what I'm going to do is that I'm just going to draw the vectors. So I'm going to draw VTG here, and then I have the velocity of person regarding relative to train upward. Okay, so the velocity of the person relative to the ground, or VPG, person relative to ground, is equal to the velocity of the person relative to the train plus the velocity of train relative to ground. Okay, but in this case, not both of them are in the same direction, but one of them is in y direction and one of them is in x direction. And this doesn't matter because this is the vector summation. Okay, so I can write this to be the velocity of person regarding to train is in y hat direction. So I can write this to be 0.24 meters per second in y hat direction plus, and then the velocity of train relative to ground is in x hat direction. So plus 0.68 meters per second in x hat direction. Okay, so if I want to find the magnitude of VPG, I just need to follow this equation. VPG equals to square root of 0.24 meters per second squared plus 0.68 meters per second squared. And the answer is 0.72 meters per second. Okay, so this is the speed of the person relative to the ground. Now, what about the direction of the person? What happens to the direction? Let me go back and draw the vector here for you. So this is the resultant vector, or VPG. Okay, but what is the theta here, right? What is the direction here? So again, so that is going to be tangent inverse of y component to x component. So theta is going to be tangent inverse of 0.24 meters per second, because this is the motion in y direction, divided by 0.68 meters per second, which is the motion in x direction. And then the theta is going to be 19 degree. So this means that the person at the end is going to, relative to ground, you see the motion to be something like this. So with theta 19 degree here. So this brings us to the end of chapter 3 and unit 1 of this course. So I'm going to post everything else that you need to study and do for this week.